extra medals today. It's another nice day, isn't it? I want to do Gambler's Ruin today. So talk about Gambler's Ruin a little more. I guess we talked about it last time. Okay, here's what happens. I'm gambling with. I start off with W. I'm gambling, and my wealth is changing. Oh, I'm almost ruined, and then I'm going to make it, but no, not quite. Almost make it, and then okay, I lose. Okay. This is x of t. Okay, so we're going to be, the interesting case, which we didn't get to last time, is when there's drift. So this is, we're gambling, and you could think of it as a random walk, but it's, I mean, the model's going to be that it's Brownian motion. There's some drift, might be zero, might be positive, might be negative, and we're starting with initial wealth W, and we want to know, so the two questions would be, so we'll define the quantities. T is the first time such that x of t equals W plus x or 0. Right? So it's the hitting time of either we get ruined or we win x. We want to know whether we win x or we lose. Then we want to know, that's the time, so we want to know P, the probability that x of t equals x. Let me see, I better be careful here. X of t is this. W of t equals W plus x of t. So x of t, this thing starts off at 0. So my actual wealth, W of t. Okay. The wealth, this is my starting point, and this is the change. So let's see. X of t, my wealth. So that's the same thing as the inf t greater than or equal to 0, that x of t equals minus W or plus x. Okay. it's as usual, but this is even more so than some things. Is there's a certain theory sitting here that we've been talking about, but with this theory, then you're doing some calculations. So if I'm doing calculations, I may screw up. So it would be to your interest if you see me doing the calculation wrong, point it out. So we'll like I'm just now having, I mean, if I do this definition wrong, let's think about all these processes. B of t is standard Brownian motion with zero drift and no diffusion. So standard Brownian motion has, at time t, has mean zero and variance t. So that's our key ingredient. We're building this out of Brownian motion. We add a drift term, and we multiply to get the standard deviation term. So this random variable, x of t, is distributed as normal. There's the mean, the drift, and the variance. It's the Brownian motion, so B of t is distributed as normal 0t. So here's standard Brownian motion, and then this is Brownian motion with drift and diffusion. And then the W of t is just that we started off with initial wealth W, and then we're going to go to either to 0 or we're going to win x. Okay, let's see. So t, capital T here is a random variable, which is the hitting time, but we either win x, we either win x or lose W, or we reach W plus x or we get ruined. And so we're interested in the probability that we win and the expected time for this game to last. These are sort of two simple, relatively simple things that you could compute from this. Okay, so this thing. Well, and we want to compute that starting right here. We're not, once we get here, of course, chances of winning looking a lot better, at least at this point, going forward. But we're thinking of the situation from here. So we're computing this from the beginning. So this is not evolving. This is just right from the beginning. And I guess the obvious thought is that things that you're going to want to think of, just to think how P is going to change if you make this probability of winning is going to go down as, say, x increases. Probability of winning is going to go up as W increases. Probability of winning is, so you can start to think of all these things, right, of how this will change. So if you started up here, if there was a small x, your chances of winning better. And moreover, if you had a lot of initial wealth. So you want to see the obvious. You should have some intuition about these things. But, okay. Now, we actually talked about this last time. So we did this is sort of repeating last time. Yeah. Probability go down as x increases. Seems good. Okay. Yeah. Okay, good. Thank you. Good. This is a minimal thought process of what's happening, right? Okay. Yeah, so if you're closer, I guess I'm thinking, I was thinking of the W for fixed W. I was thinking this way, but that's actually the x should be here, right? Yeah. So it's actually backwards. You should see. So so I guess the thought would be is your intuition. There's nothing going to happen here that's counter to your intuition. So your intuition about what ought to happen is a good guide. And when you do the calculations, you ought to check that it's doing what you think. And so the x is this distance here, so your chance of winning is if this distance decreases, it's going to get better. And if this distance, your initial wealth increases, you ought to be better off. because whatever the drift and variance is. Of course, if the higher the drift is, it ought to be more likely to wind, right? So P should increase as the drift increases, right? If your rate of the process is going up more, then you're going to more likely hit the top. Yeah.
So I think when X increases, then the probability of winning is less, right?
Yeah. So that was so P goes down as XD. So this is W plus X. So as this distance decreases, your chance of winning increases. So P goes down. I had it right the first time. P goes down. Probability probability of winning goes down as X. Yeah, that's right. Yeah, okay. Yeah, I mean, I guess we're thinking about it's this thing that's X, and we're just getting confused about whether this is, which it is, right? Just thinking about it. This increment is X. If we make this increment smaller, our chance of winning is going to, so if we make, or if I did it all increasing. P increases as W increases, U decreases, and then X decreases. Yeah, and all that's sort of obvious. But what we want is exact formulas. And actually, this was the obvious, this is kind of following last class. The sequel was mainly, the point was, well, what happens if there's drift? So that's the main thing I want to do, which is this is an analog of Gambler's Ruin for the symmetric random walk that was in the Markov chain chapter that we didn't deal with too much. So you could approach that in exactly this. It'll be a discrete analog of this, but it's the same kind of approach. Or you could do what's there in that section for that and take a limit. So you could approach this from that. Okay, well, so we want this P, the probability we win, and we want the expected duration of the game. Now, just like last time, the approach to this problem, well, there's several ways to approach this problem. One of which is to use martingales, and that's what I started talking about last time. And so we're going to do that some more. So we have martingales. And these are discussed in exercises 16 to 24 in the book. And this problem is also discussed there. Okay, let's see. So there's the high-level view of this is that there's a bunch of martingales around related to Brownian motion. There's 3 standard ones. So first point is 3 basic martingales. And we use these 3 martingales to solve this problem. We use all 3 to cover the cases. So one is the linear one. The second one is the quadratic one. And the third one is the exponential one. So the linear one is just b of t. The quadratic one is b of t squared minus t. And the exponential one is e to the theta b of t minus theta squared t over 2. So there are the 3 martingales. Now, I guess one thing to talk about is why are these martingales? What are martingales again? We talked about that a little bit last time, but here are these 3 martingales. Then the thought is, how do you think of that to this problem? So maybe before, there are these 3 martingales, and we'll talk about why they're martingales in a minute. And then maybe the thought is, how do we do this problem? So we want to know P, and we want to know the first time. So we can make this table. that says, let's do the no drift case. No drift case, mu equals 0. Drift case, mu not equals 0. So these two cases are treated differently. As you would imagine, the no drift case is much easier. But here, for Brownian motion, this is standard Brownian motion, it has no drift. So somehow when we want to talk about the drift case, we're going to work with these same martingales, but just transform it into x of t. Okay, well, so this table sort of, just to summarize what the approach is, which is a little confusing, because with no drift, everything is straightforward and kind of natural. You start with the linear martingale, and that gives you p, and then you apply the quadratic martingale, and that gives you the expected time. And we did this last time. Over here, when you have drift, it changes. You use the exponential martingale to get p. And afterwards, you use the linear martingale to get expected value of t. Yeah? Yeah, you can't. Okay, well, what is that? We don't need. Okay. Does that help? The top, oh, this thing. There we go. Yes. Okay. How's that? Good? Okay, yeah. This would be nice if this board really moved, but anyway, it does move up. We can get it up. Okay. Okay. So, I mean, the main message here is there are these three basic martingales, and these are used all the time with regard to different processes. You take a martingale, well, so in particular with Brownian motion, you get these related martingales. And here, the thought is, well, the main message is you use these three martingales somehow. I mean, you know, high-level picture is you plug these martingales in here in the right one, and you'll solve all these problems. Sort of high level is you just plug one of these in, and the thing that's a little confusing when you want to remember this story, the story isn't the same everywhere. So you might think, well, I always do this. You might think I should do this over here, and you don't do that. So that actually linear is used here, quadratic is used here, exponential here, this way. So it's actually a little strange. So there are two problems here. There's three problems. Why are these martingales? What does that mean? Why are these martingales? How do you think of this? How do these martingales, when you do these steps, how does it give you the right answer? And then the third thing is all the arithmetic to crank out the answer. Okay? But there's a sort of step of why are these martingales, and how do each of these. And the procedure is you first do this, use the answer, and then do this. Same way here, you first do this, get this, use the answer, and do this. Okay? Okay, well, let's see. So this picture's clear. I guess we can do without this, and maybe. Now this is a little bit, I'll just comment, a little commentary, this is a little bit of a strange subject because the answers sort of drop out of the blue. It sort of has a feeling of tricks. So that's a little bit, for me that's dissatisfying because it's a little bit not so compelling how you would think of this to begin with. It's a little bit like you plug in this thing, this hammer here to do this thing, and how do you know in advance that that's the right thing? Is a little unsatisfying. I mean, and it remains unsatisfying after you understand this. So that's kind of maybe the point that I'm trying to make. It's not as quite as, there's a certain element where this is a trick. Okay, well, let's just remind ourselves about the definition. So a process so we're going to have y of t to be some martingale. If it's going to have it's got to have finite means because we're going to talk about, this is a technical condition. It's got to have a finite mean, but what the real condition is that you condition on the past of the process, but you could have it martingale with respect to some other process. Now the reason for this y of t is a martingale with respect to z is we really want to talk about these three processes as being martingales with respect to the history of Brownian motion. So we make up these functions. We want to check the definition. We want to say we're given z of r for 0 less than r less than or equal to s less than t. So we're given some history, 0 s t. We're given the history here up to s, and then we're interested in what happens at t, and that is y of s. So the expected value of y of t, given the history of z up to s, is the last value of y. So you're saying, well, my expected, given that I know everything up to s, my expected value of y at t is just its value at s. So there's no expected gain. It's kind of like from an expectation point of view, conditioning on things up to s just tells me this is what it was at s. Okay? So these things, we're going to want these to have this property. In our case, this is a function of Brownian motion, and this is the Brownian motion itself, the history. So one of the obvious conditions you want to have from this is an obvious condition. This is a necessary condition. The expected value of y of t should be the expected value of y of 0, because it should have there's no expected change. So that's sort of the minimal thing that you're doing here. You're actually doing this, you actually consider this column, and you think about the expected value of these, and you do some constant adjustment to make sure that this simple necessary condition is met. So these things this is b of t, this is b of d squared, this is some exponential of b of t. You start with the simple functions, and then you do some deterministic adjustment to make the condition right. So these are easily constructed, not from any elaborate analysis, but just to make the mean right. Okay? So let's think about that in terms of this. We want, what is this? So this is the point, is then you want to be able to evaluate it. This is the second moment of Brownian motion, but it's got mean 0, so this is just the variance of Brownian motion. But that's just t. So therefore, we take this squared and subtract t, it's always got mean 0. Starts off at mean 0, starts off at 0, and has mean 0 all the time. That doesn't prove the martingale property, that just shows, that's kind of intuitively clear that that's what you need. You start with this thing, and you subtract something, do something here. This is not exactly a subtraction because this is all in the exponent. But you're adjusting this deterministically. Okay, let's look at the other one. This is less obvious, so let's look at this. We now want to do this. We're looking at this expectation. Here we have this we make this exponential of the Brownian motion with some constant theta. And we want to now know that this is right? So we want this, in other words, we want this to be what it would be at 0, but if this is 0 at 0, so then this is 0, so then this is just a constant, e to the 0, this is 1. So we want then to adjust this so that its expected value is 1 for all t, so we're going to make something e to the theta b of t minus some function of t that's going to give us this expectation is going to be 1. Okay, that's sort of our goal, and we want a simple function f of t that does that. So what we're going to do is we're going to, just like before, we're going to evaluate this. Yeah, in this case, the expected value here at 0 is 1. So let's see. So wait, am I saying this right? Yeah, this will be, this thing is 1. So if I do, yeah, so if I do, let's see, let me make sure I'm doing this the right way. I mean, this exponent's going to be 0, so then I have e to the 0 is, let's see. So I should have e to the 0. Wait, this is bad here. Maybe I'm writing the wrong. This is a little nuts here. I want to do this. Let's see. I'm being a little bit. Maybe the way to start is to say this, because this is not going to be equal. This is not going to equal this. So this isn't possible. So I've got to adjust this. Yeah, this is where I'm writing nonsense there, which is going to be easy to do. Okay, so I want to see what this is and then adjust it so it's the right thing. So this thing, just observe that this thing here is e to the 0 equals 1. So this thing starts off at 1, and I want it to somehow do the right thing. But that's this thing. That's this thing. Okay. Now, the point is, what is this? And this we see is just the moment generating function. This is, by definition, the moment generating function of this. And if we could write that this way, because the distribution of b of t is normal mean zero variance t. Okay, so we will look at that. We might know this as e to the theta squared t over 2. That's because if we have the expectation e to the theta normal 0 sigma squared, this thing would be e to the theta squared sigma squared over 2. Okay, but that's knowing that. Let's look at that here. So what I want to do now is actually look at this a little more detail here, this thing. And we want to see why that's so. So you could proceed to derive that. So all we're going to do now is see that the moment generating function of the normal is this simple exponential of a deterministic thing. Okay, so if we do that, well, let's see. So let's focus just on the case of, we'll put some variance here, and we want to do this moment generating function. Then this thing, if we just proceed to calculate this, so this is just the expectation of a function of a random variable. So we would write this down as e to the theta x f of x dx PDF, right? This is e to the theta x, and then this is the PDF of the normal. That's just the expectation of a function of a random variable. Here's the function of the random variable, here's the density. So we would write e to the theta x, and then we would have 1 over 2 pi sigma squared e to the minus x squared over 2 sigma squared dx, because we put the normal density with the variance sigma squared. here. And then we would see this exponential, and we're going to do a trick. We're going to write this, and we're going to arrange this so it's quadratic in the exponential. So we're not going to actually do any messy integrals here. We're going to arrange it so it's inside. So you put the 1 over 2 pi sigma squared here outside, and you're going to have e to the minus. We've got x squared over 2 over sigma squared, and we have this theta x, so this is minus theta x. And if we put this would be sigma squared. Yeah, okay, 2 sigma squared, 2 theta x sigma squared. Okay, so this was x squared over 2 sigma squared, this term. And then this is theta x, but I've multiplied and divided by 2 sigma squared, and this is plus here, so the minus here makes this thing. And then I complete the square. So I then complete the square and have sigma squared over 2 sigma squared. So everything's over 2 sigma squared. X squared sigma squared squared. Right? So I'm just doing this. This thing looks like e to the minus x minus theta sigma squared. Doing this squared over 2 sigma squared inside. So point is, I want to know this expected value. It's this moment generating function. I write the thing out and then have these exponential terms, and I complete the square inside the exponent, and I get a standard square here. So this is a normal density. I just replace it by 1. And so I have to put this term outside. So e to the minus plus, so it's minus, so it's plus e to the theta, what I added here, e to the theta squared. Okay, let me, sigma squared for 2. Yeah, I've got this thing I've got to put outside. So I've got theta squared, sigma squareds cancel, so I've got one of them here, and over 2. So I've got this, I have to put this term outside, and this was minus, so it's plus here. So this thing is added. So what I'm left with is e to the theta squared sigma squared over 2 times 1, because the integral is just the integral of a probability density. This is the normal density with some mean and the same variance we had before. So you just complete the square, produce an integral of a probability density, and this is what's factored out, and that's the value. That's the moment generating function, which was put here. Then in our case, this is e to the theta squared t over 2, because sigma squared is equal to t. Okay? So we see that e to the theta, this expected value, is equal to, so then if you write this thing is going to equal 1 for all arguments. And well, what we're doing is we're dividing. We've got e to the theta b of t right? This is the expected value of this is this. So we've made this 1. So all we're really doing is we have this thing we're interested in. We compute its expected value as a function of t, which is this. So we divide by it. Now it always has expected value 1, but dividing means the exponential of minus. So this thing that looks like what we had here, e to the theta b of t minus theta squared t over 2. this part here is such that the expected value is all 1. That's where this comes from. And you could have rewritten this as e to the theta b of t over e to the theta squared t over 2, right? That's just writing that another way. And this part has expected value this, so it's expected value 1 all the time. All you're doing is just doing that in a simple, this process, Brownian motion, has all sorts of independent and stationary increments, so the desired martingale stuff is going to hold. But you're really, from an applied point of view, you're just making sure that the expectation remains constant. Okay? Each of these steps, you would have, if you do this enough, all these steps you would just remember, and not, you would remember that the moment generating function is, that this is the same thing, that distribution is this, and you would remember that it's e to the theta squared t over 2. You would just remember that, but then this would tell you what you want to subtract. So then you have e to the theta b of t minus theta squared t over 2 is a martingale. Now, that actually is something else. We haven't actually shown that, so let's do that. So what would we want to show? We want to show that the expected value of e to the theta b of t minus theta squared t over 2, that this thing conditioned on Brownian motion up to s, but where s is less than t, is equal to e to the theta b of s minus theta squared s over 2. We want to say that the expectation of this process conditioned on the Brownian motion up to s is going to be this thing, a value with t replaced by s. Okay, now that's this is the martingale property that we're actually verifying. We want this. So if we look at this, we can write this. So then this is sort of the standard step that when you're doing these problems, they're all of this form. You want to use the independent increments property. So you want to write b of t as b of s plus b of t minus b of s, right? You want to do this because b of t is b of s plus this increment, and the b of s part is known, and this is what's not known. So then if you rewrite that, let's do that over here. This guy, if you rewrite this, you're going to have the expectation of e to the theta b of s plus theta b of t minus b of s minus theta squared t over 2. That's writing the same thing. Now we're using, okay, we have an exponential of all this stuff. That's the product of the exponentials. E to the theta b of s. Got all the conditioning stuff. Let's just leave that there. E to the theta b of t minus b of s. And then I've got e to the minus theta squared t over 2, given this history. When we conditioned on the history, this part is known, so it factors out. It's given. That's part of the history. This is a constant, so we've got this e to the minus theta squared t over 2. We're left with this part, the expectation of this. But having made this increment going from s to t, it's independent of the history, so we don't need it anymore. So the history drops out. This is the same as if it was t minus s. So this part is e to the theta b t minus s. The increment is of length t minus s. We can shift it. So this thing is what we just evaluated before. So we're getting e to the theta bs, that's the first term, e to the minus theta squared t over 2. And then we have this, which we just evaluated, which is e to the theta squared t minus s over 2. And then the t terms cancel out, and you indeed get as we wanted. Okay, but all you're really using is, once you see b of t here, you replace b of t by the previous b of s, which is known, plus the increment, which is independent. So this is just like when you're asked to do this. All these problems are the same. They're like all the homework problems are of this form. You want to know the expectation of this product where these arguments s is their positive times where s is less than t. How do you approach this? You write this as b of s. You write this exactly like this. One term will give you a square and the other give you b independent. That's exactly all these problems you do. You exploit the stationary independent increment. So if you see this here and you're given b of s, you write b of t of b of s plus the increment. This piece is the same and known, given this is deterministic and this is independent. So the history doesn't matter. And then you do the calculations and you get this. And they're all in the same way. Okay. Hopefully the flavor of this, not a too bad flavor, but hopefully the flavor is being conveyed. Okay, so you've then found that you've got here and you've got this is a martingale. Oh, that's what we've just went through. So there's a standard, also a very standard recipe for how to use this fact to solve the problem that we want to do. We want to get the p. And there's a standard approach, and that is to use the optional, this is what we did last time, the optional stopping theorem. So we take a stopping time, and we have a martingale, and let's say we have a martingale, y of t is a martingale. The important point that we're going to be applying is that the martingale stopped at a random time has expected value the same as the expected value at 0. So in our case, the stopping time is the time to hit one of those two barriers. And we're going to use the martingale we just found. So this is in our case where we were going here, we're starting here. The time to hit either here or here is the stopping time. And the technical definition is the stopping time should depend on the process up to the time in question. So this t, if t is the fact that t is less than or equal to t should depend on the process y up to time t. So it doesn't depend on the future of the process. So it's like you're gambling and you can decide, you're playing many sequence of games, and every game based on the past, based on what's happened so far, you can change your way you're going to bet. But you can't bet based on future knowledge of the thing. So you're just going along, going forward. So most things you would think up are stopping times, but anyway, this is depending on the past, and that's in this process. Whether you hit one of these barriers depends on the process up to the time you hit it. So that's the stopping time. And then you just do this. You write this down. So you're then going to just write down the expectation of e to the theta b of t minus theta squared t over 2 equals, now at 0, this is e to the theta 0 equals 1. So this thing, as we discussed before, this thing is 1 at 0. But now we're just going to, now that's, so this, then you just calculate this. Okay? Now, the point is, okay, this is here. So we got this, but we don't want that. So we remember we want x of t. So our process has standard deviation, sigma, and has this drift. So if we rewrite it, Brownian motion equals x of t minus mu t over sigma. So we're really interested in x of t, but all of this is applying to standard Brownian motion. So we want x of t instead. So we got Brownian motion in terms of x of t, so we just plug that in. X of tau minus mu tau okay. Now, so be careful. X of t, x of, okay, so the b of t, capital T is x of t minus mu t over sigma. Theta is still here. Okay. Now, now this is the process we're really looking at. So now we're getting to the point where we can do something, but let me rewrite this. We want to simplify this. This is all of this stuff is in the exponent. Remember, this is in the exponent. And this is to this. This here, but the whole thing is in the exponent. We had this was all in the exponent. Okay, now the point of this is an exponential of 3 terms. The trick is to not choose the theta to knock out these last 2 terms to make it simple. I mean, here's t in both cases. So you want to say, so you've got theta mu t over sigma, and you want that to be equal to theta squared t over 2. This is negative, so so you want this negative to be equal to this positive. So you want this, and then you can choose minus 2 mu over sigma squared, I think. Let's see. So if we do this, we're going to get minus 2 mu squared sigma squared t. And here we're going to get 4 mu squared sigma squared over 2 t. So let's see. So am I doing something? Yeah, let's see. So plus okay, right? This is minus, so this thing should be minus this. I want one of these to be minus, and therefore, so I had the sign wrong here, and so these things are the same sign. I want them to be different signs to drop out. And so this becomes negative, and this becomes, so I want this, so when I do this, I get the right thing. Okay, so let's see. I've got these are both initially minus. when I put theta squared, this remains signs unchanged, but when I make it negative, this becomes positive, this stays negative, and they're the same absolute value. Okay, yeah, and this should be sigma squared and sigma, because we need sigma there. Yeah, yeah, yeah. Okay, so then, having done that, we're left with, yeah, gets a little bit, you're left with theta, so e to this is minus 2 mu sigma squared x of tau t, x of t equal to 1. The other two, in this original expectation here, these two terms just dropped out by choosing the right theta. So I put minus 2 mu over sigma, and there's one sigma here already, so I get e to the minus 2 mu sigma squared x of t equals 1. Okay, here we know P is equal to, by definition, the probability x of t equals, that's the x, it's going to be plus x. And 1 minus P equals the probability that x of t equals minus w. So when we can fill that, we can write this thing down. This is P times e to the minus 2 mu sigma squared x plus 1 minus P e to the minus 2 mu sigma squared minus w equals 1, or P e to the minus 2 mu sigma squared x plus 1 minus P e to the 2 mu w sigma squared equals 1. And then we solve for P. Okay, and solving for P, we're going to get e to the 2 mu w sigma squared minus 1 over, that's putting this term here on the left. If I put this on the right, I get e to the 2 mu w sigma squared minus e to the 2 mu x. And this thing is something, x is positive, this thing is something less than 1, so the denominator is bigger than the numerator, right? Remember when there was no drift, we were sitting here. If we think of x, this is plus x minus w. This is x of t. The p then before was, you want to talk about the p as probability hitting up here, was probability of going up there was greater the further away you were. This was no drift, which we talked about last time. When no drift, we had this. With the drift, we have this more complicated thing with exponentials. There, I will make some notes that will cover this ground. I'm not really expecting that you would be reproducing this whole schmear on whatever, 2 weeks from now or whatever, but some manipulation with Brownian motion should be reasonable. This is a little excessive. Okay, so far, having done that, we found P. So we use this we used this martingale. We said, oh, here we're going to use the exponential martingale, which was squared. Here's this exponential martingale. We use this martingale, and we generate from that when we get P by sticking in the stopping time, right? Okay, now that we've got P, we can consider getting the expected value of T itself, and now we can use the regular martingale. So we're sitting there and we're thinking, well, okay, regular martingale, we have B of T, so expected value of B of T equals 0, just what it would be at 0. But now we want to stick in x here. So B of T is x of t minus mu t. So x of t minus mu t over sigma. So this is the linear martingale, B of t, and I stuck in the stopping time. I just substitute x of t minus mu t over sigma, because x is defined in terms of b this way, b is defined in terms of x this way. So where I have b, I substitute this, and that sits here. And then I have the expectation of x of t, random t, over sigma equals mu times the expectation of t over sigma. This drops out. And we're in business, although it's a kind of messy business. But you can see that, what is that saying? That's saying the expected value of t is 1 over mu, the expectation of x of t, which is 1 over mu, and then you're looking at this, you're saying, oh, it's p times x plus 1 minus p times minus w. Because with probability p, we end up here, and with probability 1 minus p, we end up w, where p has that formula here. Okay, and then you get a bunch of ratio of exponential terms when you plug it in, as according just plugging p into here. Which is actually, this is actually, I guess maybe I should have, in order to make this more interesting, it's sort of, the point to be made is that it's less obvious that what this answer is going to be. Because you're being asked here, you're sitting here with, say this is your 0, so you're thinking plus x minus w from here, and you're thinking about where you're going, but maybe you have some drift. There's some drift that's not 0. Arbitrary drift either down or up, and you're calculating with the probability that you're going to hit each of these things and how long it's going to take to do so. And that's not obvious if you figure out what this would be. And this is the kind of thing that sort of underlies all these financial calculations like option pricing and so forth, that if you've got Brownian motion and geometric Brownian motion and so forth, you're going to want to do calculations of expected values in this way, which I think we will talk about a little bit next time. Yeah, Robbie.
You put like e of x and t minus mu t over sigma is equal to cancel just e of x and t over sigma.
Yes, good. Yeah, that should be, this is just an expectation of a linear thing. It should just be like this, right? Then this is going to be the point I'm getting to. Yeah, I'm using this here. I've subtracted to get this formula here, right? Okay? Yeah, I meant to write a minus sign. And then you plug that. Yeah, there are more things. There would be easy to write surely if you make a plus sign or an equality sign or something wrong, all will fail. But at any rate, the high-level story is you have these martingales. That means you can compute the expected values, and you can solve for all these things. This becomes also interesting to think about, where you're seeing well, so much depends on if you could think about what's your chances. I guess this is, if you think about P, so we wrote this down before, now we can actually calculate. P increases as mu increases. P increases as the variance decreases if mu is positive, and as variance increases if mu is negative, which is sort of the point being, here you are, you want to get here, P, and this thing is oscillating. If your drift is up, you want less variance, because you're going to, if the least variance of all, it just go like this. So if you can reduce the variance with positive drift, you're going to get here with probability 1. So you think, oh, if I make sigma squared, now, if I make variance get small, if mu is positive, so when mu is positive, this will be the dominant term, and as sigma squared gets small, this thing goes to infinity, whole thing goes to 1. But you could do calculus to see how this changes. If, on the other hand, if the drift is negative, really these things are shifted around. And the thing is really the other way around, because this is really negative. If mu is negative, then this is positive and this is negative. So it changes around. So this thing here is like what you would think. If the odds are against you and you're going down, more variation is going to increase the chance you might, by luck, end up hitting the top. Then it's, so there are insight. I mean, there are nice insights which you can quantitatively see, like what would happen if you change all these parameters, mu and the rate, the drift versus very nicely is the business of, in this model, exactly has drift and variability as two separate parameters, the only two parameters. So you can relate, tendency of drift versus the fluctuations and variability in the problem to what's happening and how the thing's going to perform. So that you could think about, you would easily think about if you were to consider investing in two stocks and they have different rates of growth and different volatility, you could be thinking about what's your chance of doubling your money in some state without something happening. You could begin to figure out, as comparing the rates and the variabilities, those two parameters would be different maybe for both of them, and you could relate the two. In this story is pointing to looking at mu over sigma squared as a key single parameter, right, in terms of this performance. But that's assuming a constant sign of mu, right? So you could think of things. How do you think about mu and sigma squared? If you were interested in P, the ratio, mu and sigma squared enter in here only through their ratio. Okay, well, so let me just kind of as a 2-minute review, since we have a few minutes, is to think about the no drift case. In the no drift case, if we wanted P, we started with the Brownian motion and we just said this equals 0, and there was no drift term, so there could be sigma here too. If I make it then you're looking at P x, maybe sigma px plus sigma 1 minus p minus w equals 0. So let's see. So then you're having p equals divide through by sigma. We're getting so p. Okay, 1 minus p x px plus w equals w p. So in the no drift case, we have the linear martingale, which is just Brownian motion. We do the stopping time. We stick this in. We get this simple linear equation, which gets this simple formula. If we do the no drift case, and we want to know the time, the mean of the time, we're going to do the quadratic martingale. So we have b of t squared minus t is the martingale. We then have dB, let's just suppose the variance is 1. This at 0 is 0, so we get ET equals E B of t squared. This thing will be P, this will be P x squared plus 1 minus P w squared, right? And that's P, that's, if I go here, that's w over x plus w x squared plus x over x plus w w squared, which is wx times w plus x over w plus x equals wx. Right? So that actually here, the expectation of this time is just wx. That's where 0 minus wx. So the product of these two distances is the expected time. So all this, in the case of the no drift case, it comes out very fast because you don't have to mess with all this. It's going to be a simple formula. It's not complicated. I mean, but you stick in the quadratic martingale, you stick in the random time t, you take the expected value right away, you get the expected value of t is equal to the expected value of the square of where you stop, which is then this. And then that produces this, which is nice intuitive formula. The expected length of time is proportional to the product of the two different distances, which should make sense. Okay. That's a sample of, this is intended to illustrate the Brownian motion type calculations, martingale's Brownian motions, typical kinds of calculations you do with Brownian motion. On Thursday, I'm going to try to talk a little bit about option pricing in the Black-Scholes formula. So that's geometric Brownian motion and the Black-Scholes formula, which is one of these things of a stopping time related to geometric Brownian motion. So there's some of that in the book also. Okay, lunch.